Good afternoon to all of you. So we have already done this one-dimensional box, and the motion of a particle which is trapped in that box has been analyzed in great detail. We so one thing that you have must have observed that these are all the wave function that we are drawing are representation of something of a like a standing wave. It looks uh, like a standing wave which is formed on the string when it is tied at both ends. So the all the profiles that you see is just like that. Number one, and then we also saw that as the expression for energy we have tried to find out in two different ways. One was simply fitting that standing wave, one, two, three, and so on, three half waves, four half waves, such that the boundary conditions are satisfied and all the postulates that we have learned. So it is also following that. Then we find that it is simple fitting the half wave. We find it very easily. We can see a trend emerging from that, and yes, then you can find the energy. And to have a even more greater idea about it in detail, if you not just energy, you want to find the coefficient, the normalization coefficient, and all that, then we have to go a more elaborate pathway, which we did by following the analyzing the two, applying the two boundary conditions separately. So the value of C was evaluated, and we found that it was coming out to be something like this: under root 2L sine n pi L x. So this was for one dimension, and this was the expression, how does the energy level diagram will look like. So corresponding to different, so we see that spacing increases gradually as we move to the higher quantum numbers, and if the L becomes too large, then it will, the blue shading that you see, for that is L tending to infinity, all of these will vanish. The separation between the energy levels will become less and less if the length of the box becomes larger, and when it is infinite length, then it will be a continuum shown by this blue color. Okay, so these points, and while 2 3 points, quick points, because most of the time when you write a subjective answer in end term you make mistakes. So I'm uh, asking you to uh, have a great look at minutely in this structure. The amplitude will remain same, the wavelength will vary. Okay, and so the probability at different points is getting changed. And we also see that as we move to the higher numbers, there are more number of points of equal probabilities. So at very high quantum number you can expect that almost all the points there is equal probability, so you become uncertain with respect to the uh, yeah probability sorry, position within the box. So uh, So you also see that the curvature goes on increasing. So you have, as the number of nodes increases, you have the curvature becomes sharper, because you have to make the function smooth, continuous. So all these requires that you must have a sharp bending, curving curvature should be there. So that was indicates towards increase in energy gradually. And so linear momentum sine kx is not so the function that we have just found, we found for the particle in a one-dimensional box is a cosine wave, sorry, sine wave, and the sine function is not an eigenfunction of momentum operator. So we have to we can, to find the momentum, we can express it in this way using the Euler's theorem. And so if you write it in that way, it will mean that you can half the measurements will give you minus kh cross, half the measurements plus kh cross. So equal probability of the particle finding the particle traveling between plus and x. So that means it is a classical view of that will be that you have a box and the ball rattles, is undergoing a rattling motion, bouncing from one end to the other wall, one, so wall to wall, bouncing back and forth, kind of thing. All these things plus the lowest possible energy, the 0 point energy. So this was also discussed. The energy that always remains with the system, which you cannot remove by decreasing the temperature or by any other means, is 0 point energy. So this energy, this amount of energy remains with the system, and even if you take it to 0 Kelvin, so that's why we call it irremovable energy, and that's precisely the reason it is also called 0 point energy. That the energy doesn't become zero by any means, anyhow. You cannot reduce that energy below that point. So the origin was explained in two ways. One was the Heisenberg principle. The location of particle is completely so within the length of the box is definite L, and within the box the particle is somewhere there. So the location of particle is not indefinite. That means uncertainty is not equal to infinity, and that means the momentum cannot be precise. The uncertainty with momentum is not zero. So which means that when you apply the equation which we found, we earlier discussed regarding how the uncertainties are expressed, then this is the case that we can. So this is the way that you can have it. So the second term can be, this term can be zero, but this can never be zero. So that means del p is there must be certain momentum. If momentum is there, then kinetic energy will also be there. Then you can argue in another way that the necessity to the function has to be zero at the two ends and at the two walls, smooth, continuous, and not zero anywhere else unless it is a node. So then the function must be curved. It has to be curved, and curvature means energy. So the minimum that we can make is one bend with a bend kind, that arc that we draw. So that is the only least uh, the possibility that we can have. Okay, so having done all these things, we have also analyzed this difference. Is a simple extrapolation of that thing what we have, energy expression of energy, that two successive energy levels n and n plus 1 can be analyzed, and the separation between them can be found this. And so you can see that as hmm, so this point I have already discussed, walls are infinite, L becomes infinity, then this separation will be gone. It will look like continuous, negligible separation. So yeah, so this we can apply in a problem like this, where you have a conjugated chain. So along a chain, so this is the electron. Imagine p orbitals of these 22 carbon atoms overlapping in sideways manner, forming our orbitals. So you can have delocalization of electron through this to this end, and this is a kind of a box that you can imagine, one-dimensional box. The electron is making moving in which it is moving. Electron is moving. So with that kind of visualization, you can form. You have to find the uppermost orbital. So there will be 22 carbon atoms forming 11 bonding and 11 anti-bonding orbitals. So the total number of electrons is 22. So 11 of them. The first, that is occupied, and so you have to find the next one, that n, the LUMO is n plus 1 is 12. So simply work out the details and you get the answer. Similarly, you can do this for this thing, and the probability densities profile. So this was also this. So now we are in a position to move to the next level, that is particle in a two-dimensional box. After having discussed all these things in detail, so analyzed all these probabilities functions. So this is the psi and psi square on the right hand side. So you can see the pattern that is emerging is that you are having more number of points which are of having equal probabilities as you move from 1, 2 and 3. Initially there was only one point where maximum probability was there. Now you have 2 points on the both sides of this central location, and now 3, and so on. You will have more and more such points will be there. Now we are in position to discuss for motion of particle in two dimensions. Again, we are so you can imagine. So you can think of just like we had one-dimensional box of length L. Now you will have length L1 and length L2, and so and the walls that you see are again having very high energy of rising up to infinity. So L1 and L2 are the two lengths along x and y. And an exceptional case would be when you have L1 and L2 is both equal. So let's start with that. That is the simple case. You can imagine a rectangular box, and the rectangular box becomes a square, well, if it is the both lengths are equal. And so particle confined to this plane by two walls along x, two walls along y. So you can think of the motion between these three things. So potential energy has to be zero inside the wall. It is inside the box, particle is having zero potential energy, and at the walls it is infinite. So you can write the Schrodinger equation. Now here uh, so now the difference that you have seen from as compared to first one-dimensional thing, here now we are writing in form of a partial derivative. We are writing because now it is a simultaneous function, uh, partial derivatives. Okay, so it is in that form we are writing. We are not straight away writing and not writing as d2x by d2 psi by d2 square, not like this. So we are not writing this because now psi is simultaneously a function of x and y. So when such things happens, you have to write in form of partial derivatives, and the sign is now not d, it is del square like this. Okay, so this is the way in which we write whenever we have one function which is uh, the psi or any mathematical function is dependent on two variables simultaneously, x and y in this particular case. So इसलिए हम इसको यहाँ पे ऐसे लिख रहे हैं. ध्यान देने की बात ये है. और so because they are moving, so the overall motion can be bifurcated. You can in two dimensions in along x and along y can be seen as a moving along x and y. So you can also have two kinetic energy terms, for one for each axis, and then you can define overall energy in a region. Okay, so this is a partial differential equation. Yes, who's that? क्लास लगेगी सर मैं 4 बजे आता हूँ. फोर्थ नहीं, मैंने 3:30 को स्टार्ट ही किया है. 4:30 तक. ठीक है सर. थैंक यू सर. ओके. So so this is your equation. We start the story starts from here. The potential energy is 0, so there is no v term coming in over here. So we can write, and this, to simplify this equation, we have to find a way such that two functions that psi is a function of x and y, and can we what our intention would be to split into two such functions, which will, if we multiply the two functions, they will give overall psi. So something like that can be divided into two or more ordinary differential equation. That is, one function which depends only on one x, another function that depends only on y, and when we multiply these two, uh, we get the overall psi. So something like that, if we can find out, so that is what we try to do. We will try to find that a function something like capital X, which is only a function of x, and some function which is y, which is function of only y, such that psi xy will be equal to x y. So something like that we are trying to, so we are, our imagination takes up to imagine something like this, which we can, if we can do, it will be good for further understanding. And function 1 multiplied by a function 2, so in this way we are able to split. And so this is our intention, would be to do something like this. Whether it can happen or not, we will see. So so mathematically it is possible. So fortunately for us, it is helpful, we when we do this. So whether a solution can be found by writing the wave function as a product of functions. So this is what we are trying to, we are trying to find two wave functions, one depending only on x, one another depending only on y, and when we multiply these two, the product is psi. So this is our intention, and to do this, and then those should also satisfy the Schrodinger equation. So, so so when, so what we first, we think that x is independent of y is independent of x. Then if that is possible, we can possibly write these partial derivatives into something like this. So psi, which is x and y, from here we are substituting the value of psi x and y. So because when the differentiation is with respect to x, y is unaffected, so y is taken out, and d2x by dx square we can write as a complete derivative. And similarly, when we are differentiating with respect to y, x remains unaffected, and we can possibly write it like this: x is taken out, and d2y by dy square, a complete, so which was a partial derivative, we are now converting it in this way. And so we have two equations, 1 2, so only on x, depending on x, and one on y. And then we substitute in this equation. So when we try to do this, where of course we are having this psi is equal to xy, then equation becomes, so replace this psi with xy, and these two partial forms, this one is substituted from here, and the equation will look like something like this. Next we divide both sides by x and y, xy. So we do this, then the equation becomes, right hand side is now totally freed from x and y terms. Right hand side is completely clear. You can also note that now the right hand side is a, for given function x and y, it should be constant. Right hand side becomes constant if x and for given set of x and y. So you can see that first term on the left is independent. This is independent of x. So this term is independent of independent of y. So if we only vary y, then second term can change, but the left one should will not change. So because this is independent, unaffected by change in y. Okay, so this term, if only y, if suppose y is varied, then it is unaffected by change in y. Now the second term can, if that changes, uh, so if you look at the second term, y changes, the whole term, this the entire term is, so when the small y changes, the whole term may change because it is a function. But if changes, अगर ऐसा होता है तो राइट हैंड साइड को आप देखेंगे तो राइट हैंड साइड कांस्टेंट है, इसका मतलब ये भी नहीं चेंज होना चाहिए. So in this case, if the whole term may change, but if it changes, then you will also have a change in the product overall result, and it will not be constant. Changes the right hand side, the RHS will not be constant. So which means that this term should, so then our equation will not be valid. So even this second term should also be unchanged, it should also remain unchanged. So this is, so when you argue in this manner, you come to a conclusion that both these terms, the left hand side terms, first and the second, both must be a constant term. Otherwise the right hand side, which is represented by a constant, this is constant for given wave function x and a given wave function y, capital Y. So to keep the right hand side constant, both x first and second term should not change. To keep RHS constant, what turns out to be both the terms on LHS, both LHS terms, left hand side terms, must be kept constant. Only then this equation will be valid. So keeping this in mind, we can formulate it this way. We can put it like this. So sum of the two terms is a constant given by the RHS right hand side. So if the first term does independent, ये तो हो गया. अगर सिर्फ y को हमने consider किया, उसी तरह से right hand side will not be constant, and which implies that this must be constant. Even the second term cannot change when y is changed. And so in other words, we must represent the second term as a constant like this. So this is the energy along the y that we can say a second term is reflected through a term which is energy, kinetic energy due to the motion along y-axis. And by a similar argument, assuming that we are changing the x variable x and arguing in a similar fashion, we can reach the conditions that okay, take. So by a similar argument, so now if another way of arguing this thing is that suppose x is being varied, then only first term will change and second term remains constant. But if first term changes, then right hand side will also change. So to keep the right hand side constant, even the first term should also be treated as a constant, and this constant must be equal to something like this. So this is a term Ex that you are seeing is the energy, kinetic energy uh, along due to the motion along x-axis. So the whole idea then comes out to be that total energy E on the right hand side is equal to summation of Ex plus Ey, and so we can write the first term as being equal to this, the second term, so x is the superscript subscript, sorry, थोड़ा सा इसमें छूट गया टाइपिंग में थोड़ा सा मिस्टेक है, so it is a subscript that you should take E as the subscript, not a multiplication sign. Okay, so treat it as a something this way. So like this. Okay, so we are treating them, so one side, so what we have, what it turns out to be that so we can write it this way. So this term is a constant, is minus 2 m e x by h cross square and minus 2 m e y by h cross square something like this will should be equal. So this is the terms, so making the two terms constant in this manner, and then the right hand side is also constant. So this is what we are making out to be by considering them. So by a logical argument mathematically placed like this and balancing such that the equation is valid, this happens, and we can write it in these terms that both are independent of other variable, one of, so we can make two different separate equation, each one of them indicating just like a particle in a box. So now we have separated original equation into two different functions, one having showing a variation as per x, another showing variation of amplitude along y. So both the motion can be defined in separately, and then we can write the equation, the Hamiltonian in this. So Schrodinger equation can be, one Schrodinger equation is now separated into two for each of the motion along x-axis and along y-axis, and in this manner so both are both the differential equations are same as the Schrodinger equation for one dimension. So, and the solution for one of each one of them can be written in a similar way to be like this. So along x you have 2 by L1, along y you have under root 2 by L2 as the coefficient, the normalization constant, and so n1 pi by L1 x, n2 pi by L2 y. So similar, just the formulation is similar as what we have derived for uh, particle in a one-dimensional box, but we have two different wave functions, one to define along x, motion along x, another to describe the motion along y. So the net result is that psi is a product of two functions, capital X, capital Y, and the energy is a sum of the two, Ex plus Ey, and net final thing outcome will be that the total wave function will be then shown by this. So just to put the write the two equations. So under root 2 by L1, under root 2 by L2, multiply it together. So you have 4 L1 L2 sine N1 pi. So just put it there, and the energy will be given by simply the sum of this h square n square h square by 8 ml square. So L1 square L2 square is coming over here, and N1 N2 are the two representing the series of quantum numbers that you can think of along x and y. Okay, where N1 can vary from 1 2 and so on, N2 can also vary from 1 2, and they are taken to be independent of each other. So some of these functions can be plotted here. So the overall combination of the two, the overall wave function will look like something like this. So a plus sign means that, so these are the circles that you see, they are points connected of equal amplitude. So circles, the different circular or elliptical lines that you see, these are contours which are connecting the points which are having equal amplitude along x and y. And the plus sign means that it is coming up above the screen, and if I put a minus sign, that means it is going behind the screen. So oscillation up and down, just like you can think of in a trampoline. So think of a trampoline, and you just, so a static trampoline, you have it is equilibrium, and then you jump over it, it will go down below, so that is negative, it will go up, that is the positive sign of the wave function. So this is how we assign it, and this is how we draw it on a two-dimensional frame, drawing like this. So this positive sign is that it is moving up, and or you can show it like this, two-dimensional wave function. So 1 1 means you have a psi 1 1, which means n1 is equal to 1, n2 is equal to 1. So n1 and n2 both are equal, then both the quantum number along x and y are equal, then we can show it like this. So these are the points. So this is the lowest possible energy state that when we can think of. N1 is equal to N2, both are equal and equal to 1. So uh, so these are the contours of equal amplitude that is drawn. This is what we are talking about. And if you are trying to draw it through colors, if you can see the shading of the dark shading orange that you see in the middle, that is the highest point crest that you can see, and all others are points which are having lower rise from the top, but the displacement is in the same direction. And when you have n2, one of the quantum numbers is high, is the second state, second quantum number n2. In that case, you can see there is a node appearing in between. This is a node. Dotted line represents a node, and on the one side you have up. So the two color coding and the sign plus and the minus here. What does the two represent? This is to represent uh, that on one side of this trampoline you are coming up, the other side of trampoline is going down. So up and down. Okay, so imagine a trampoline. If two persons are there and they are jumping in such a way that one is, while one is going up, other one is going down the other side. So two halves. So that kind of motion is represented by this kind of curve. So not exactly the picture, but quite to some extent a physical picture you can think of will be like this. Okay, so this is for the next energy level, the wave function profile of second one, second next energy level. When n1 is 1, n2 is 2, we can think of something like this. Okay, and you can think of when the energy would also, because it's a square, if it is a square well, then whether if you put n1 is 2 or n2 is equal to 1, in both cases you will have similar energies. Okay, 2 1 or 1 2. Okay, so the wave function for particle confined to a rectangular surface will is like this. And then when n1 is 2 and 2 is equal to 2, you can think of this manner. So it will have two nodes. Now you can see one node on this line, another node going through like this. So you can have so so plus sign indicates the surface is going up from the equilibrium position, and the minus sign indicates it is going down in that other half. So something like this can happen. So you can, your imagination takes you to this three. So first energy level, second 2 1 or 1 2, and then 3. So 1 1 2 1 represent the n1 and 2 values, which can range from 1 2 3 and so on. So values which are positive is in red, and the gray shadings represent here the negative values going down like this. Or in a more detailed manner, if I can take you through this, then this is your n is equal to 1. So n1 is 1, n2 is 1. This is the first picture that we can think of. Okay, and the next, similarly, when we are talking about n1 n2, uh, so this is the second one. What you see here, see, one is going up, other side is going down. So imagine a trampoline, one is going up, other half going down. This is the kind of wave profile that you will generate. So this is for particle in a two-dimensional box with having energy n1 is equal to 2, n2 is equal to 1, or vice versa. Okay, so the blue color means it is going down. So this is what we draw, and plus and minus sign that we indicate shown in this manner. So going to the next, when you have, so that was 1 1 and 2, so we have three situations that we had imagined, and so these are the correlations of this 1 1. So first one, when both are equal, n1 and 2. Second, uh, second is when you have 2 1 or 1 2, 2 1 1 2, or in a rectangular case you can have this kind of thing, but in a square well both will be of equal thing. And then third case that we are discussing is that of 2 n1 is 2 and 2 is also equal to 2. So these are 2 3 different combinations that we can discuss. In a rectangular case you have third combination u3 1. So in this case you have 1 2 3 like this. So what you have seen here, so basically when you will be drawing in exams you will be having to draw like this. So first case, again going back to the first one. Yeah, yes, first case when both are lowest energy one equal to 1. So imagine you have n1 is equal to 1, n2 is equal to 1, so there will be no node in this lowest possible energy state, and this is what we think of. In the second case, what we have, n1 is equal to 1, n2 is equal to 2. So imagine what you have along n2. So x and y, the way we have defined, along n2 there will be a node. So along y there will be a node, along x there will be no node. So this one, so x and y if we define, so if this is x, this is y, so along this we have no node along this direction, but when we are going to y, here there is a break, so like this. So you have a node appearing over here in this way. So this is the way you have to plan. And when you are writing n1 is equal to 2, you are seeing along this direction, along x, we are having a node in this appearance of a node. So just like that you can imagine and things. Whereas when n2 is equal to 1, there is no node along y. So along y there is no node along x, no node along y. So this is the care that we have to take. So here you saw node along y. So imagine you are having two wave functions corresponding to 1D motion along x, along y, and it is a combination of the two. So if you break it down into that way, node along y, so here you have a node along y, here you have node along x. So only it is the change of this. So this is the care that you have to take while drawing this. And when n1 is 2, n2 is equal to 2, you have nodes along both, along y, along x, along both the directions you have nodes appearing. So one node along x, one node along y. So this is the way you have to think of while writing the things. And this was the representation, and in a similar fashion when we are writing psi 3 1, n is equal to 3. So the number of nodes along x, if you assume that way, should be 3 nodes. So you show it like that. So 1 2 3 3 1. So here you see so x and y. So if you 3 1, n1 is equal to 3, so 1 a rise and the fall. So here is a node, you have another node appearing over here. So along x direction you have 3 nodes, and there is, so this is what we see here. And along y, yes, what is that? Yes, sir. Yes, about what?
So we want permission for using UV spectrophotometer. We are from Department of Environmental Science, and we need to calculate nitrogen from our samples.
So, but I do not have any staff to right now who can do that. Right now, we don't have any staff to do that, so it may not be possible.
Tomorrow,
Students, I think when at least our students should come, research scholars.
okay, sir.
So as long, because no other is having that knowledge of the systems.
Okay.
So immediately, if you ask, it is not. But in yes, in next few days, you can do it.
Okay.
How many samples?
Sir, now I have 3 samples. Sorry, 4 samples.
You both are students from EVS.
Yes, sir.
Achha.
4 samples.
4 samples. And yours?
So same.
Okay. So it will be done, but depends on the availability of staff, and even the research scholars can do. So if my students can come.
Okay. For that, so we need some kind of form. From
विशाल के पास जाके ले लीजिए, विशाल के पास होगा, उसको पता है.
Thanks. Thanks.
So this is the way you have to think, constructing nodes and in one direction and then not the in the other way. Okay, so like this, yeah, along y, yeah, along x and y. So This is the basic idea that we follow to make out this kind of structure. So 3 1 2 1 and then 2 2. So this last one you see, this one is two nodes along both the directions. You can see here. Sorry, this one. So this is when n1 is 2, n2 is 2. So along x, two nodes. So two half wave. Along y also you can see there are two nodes appearing. So two half waves in both of them. So this is an easier. It is also an easier way to describe the things. You talk in terms of half waves. How many half waves along y? How many half waves you can fit along y? ठीक है. So this is how the color coding is done. Blue indicating below the plane going down, and this, and when you write, or you can write, if you do not put so much colors, you can simply write plus and minus to show the direction. So that is the sign of the wave function, plus and minus indication that you can give. Okay, so these are the points to be understood. Okay, ये हो गया 3:1. 3 1, that means three nodes. So you have uh, two nodes along x. So three half waves are fitted along x, whereas along y you have only one and node. So along y there is no node. See this? If I am looking along y, there is no node. So n2 is equal to 1. That means a complete half wave is fitted along y. And when I am looking along x, I have three nodes. So, or sorry, two nodes, or I can say that there are three half waves fitted along this, along x. So 3 1. See, one half wave, second half wave, a third half wave, half half half. Okay, so this is the way to look at the things. It makes much easier. Okay, when you are looking from the y direction, you are having a complete one into the other with a curvature. There is no node appearing, but when you are looking along x, so this is 3:1. So looking at the pictures, you should be able to identify what we have. And this is look whether you look along x or y. In both cases, you are getting two half waves fitted. So this is a point of node that we can see. Okay. So and when you look along y, you also still have two half waves fitted. One node appears along this direction as well. So n1 is 2, n1 n2 is also 2. Okay, so this is the description. Okay, so in a similar way we can also go to the three-dimensional box, and here there will be another factor will come in where function will have another z, x y z. So z dependence, z कहो या z कहो एक ही बात है. So dependence on z or z, you can say, comes into picture, and you will have simply the n3 term will be there. So you can think of an additional term. So 3, so under root 2 by l at l1, 2 by under root 2 by l2, under root 2 by l3. So this is the three terms which have been multiplied together to get this thing. So it is easy to imagine what kind of functions we can have for a three-dimensional particle in a three-dimensional box. So x, y, and z in a similar, all sine functions. So we can have n1, n2, n3. So n1 by l1 square, n2 by n2 square by l2 square, l3 square by. So these are three terms, and h square by 8m. So the degeneracy arises when the length this L1 and L2 is equal. In this case, so this is a one case of degeneracy that we are discussing. There will be another one that we will discuss a few in later on. So in 2 and 3 dimensions, when L1 becomes equal, so degeneracy, I think, when along the two axes the energy no, you have for you have two wave functions which correspond to same energy. So it is because of the direction that we, so just let's see how it happens. L1 and L2 are equal, which is represented by L. So now we can write it in this way. Under root 4 becomes 2, 2 by L, sine x and phi. So n1 pi x by L, L, L1, L2 both are equal to L. So we are writing it like this. And the energy will become equal to n1 square plus n2 square by h square at ml square. So you can arrive to the same energy if n1 and n2 are along x and y. You change the value of quantum numbers. So whether you have n1 is 1, n2 is 2, will get the same energy, or n1 is 2, n2 is 1. 1, 2 or 2, 1. Both combinations give you the same energy. So both give to rise to same energy, but they correspond to profile of wave function will be different when you look along x, when you look along y. They will have different profiles, but their energy is same. So this is what we know as degeneracy. So so n1 n2 we have just discussed. So first, if we take the case of n1 is 1, n2 is 1, what is the energy? So you substitute the value, then you find that it is 5h square by 8ml square. In a similar way, if you suppose that n1, now n1 is 2, so 1 has changed to 2, and 2 1, something like the combination is different now, and this means that you are writing 2 pi xl here. Substitute the values, you can get this easily. So 1 2 2 1, we write the wave function as a subscript. We are giving psi subscript 2 1 or 1 2 representing the 2. And now if you calculate the energy for 2 1, uh, 2 comma 1 e, so this is also having the same energy, 5h square by terms. So this, the wave function are different, but they have same energy. So this is what we mean by we in other words, we say that the two states are degenerate. So this is the case of a square when the two lengths are equal. So we say that the two degenerate wave functions, the energy level is doubly degenerate, or we say that the energy state E12 5h square by 8ml square is doubly degenerate. So so degeneracy arises, you if you look closely into the wave functions, you will find that they are related to symmetry. You are already studying group theory, so you can correlate these things. If you can look at the pictures very systematically, very analyze it methodically. So these are the contour diagrams for 1 2 and 2 1. This is for n1 is equal to 1, n2 is equal to 2, and the lower one is for n1 is equal to 2 and n2 is equal to 1. So 2 1 and 1 2, this is the psi wave functions profile when this is like this, two degenerate wave functions. So they are related by symmetry operation that you can see. You have a rotation uh, by simply rotating by 90 degree, you perform, and you see they are converted from one to other. So you will find that wherever degeneracy occurs, they are somehow related to each other by a symmetry operation. Okay, so this will happen only if the L1 and L2 is equal, that is in case of a square. So they are degenerate as long as L1 is equal to L2. If they are not, L1 is not equal to L2, then they will not be degenerate. If L1 is not equal to L2, there will be no degeneracy emerging. So because in that case the symmetry is also gone, the 90-degree conversion that we are thinking about. So if box is square, you can convert one wave function into the other simply by rotating by 90 degree. Okay, but if L1 and L2 is not equal, the two length scales are different along x and y, they are not. So, so in a similar way, you can account for the a three-dimensional box where uh, all the lengths L1, L2, L3 will be equal. You can again have degeneracy over there. Okay, uh, there will be many examples of degeneracy that all are traced to the symmetry properties of the system. Any degeneracy, so in case of even if we go to for hydrogen atom or anything, so wherever there is symmetry, uh, if two wave functions are related by symmetry operation, then we can think of having degeneracy over there. So these are the different wave functions: 2 1 1 1 2 1 3 2 1 2 2 3 1. So all these combinations are given here. So these are degenerate sets that you have in case of if it is a square. Uh, so orange, so orange is the positive. So wave functions. If you are referring to Macquarie's book, they are writing instead of psi, they are using a word u as a symbol for the wave functions. So this is same as saying that we are having a psi 1 1, psi 1 2, psi 1 3, psi 2 1, psi 2 2. Okay, so if you now analyze in terms of for three-dimensional thing, then you have nx n square, ny square, nz square, and you can see the first one when n 1 1 1, only one energy state, only one wave function you can write having the energy up to of this. But when you go to the next energy level, 2 1 1 1 2 1 1 1 2, so this is corresponding to this particular energy. You have three different ways of achieving that energy, so the wave functions will be different, oriented differently along x, y and z, and yet having the same energy. Similarly, next energy level corresponding to combination of nx and y and z, square of these three terms, 9 11 12, you can define it this way. So you can see here when you are going to 14, you are having 1 2 3 4 5 6 6, the degeneracy is 6. So in a cube you can have in this manner you can have degeneracy, which is so 6 different ways in which you can have the same energy. So all this is so that's it. We keep it here. We will talk about quantum tunneling in later next class. So okay. So that's it for today's class. You can just think over it, and I think we can do some quantum tunneling in next few classes, and then we can start with thermodynamics, because we have quantum mechanics in the second semester as well. So we'll pick up from there up to one dimensional we will finish, and then we'll start the other part of uh, physical chemistry, that is thermodynamics. And so only one part is remaining, quantum tunneling. We'll try to finish that. So degeneracy can arise. There's few more cases in which degeneracy can arise, like if it is multiple L and 2L. If it is a rectangle, but the length scale x and y are related. So एक अगर L है और दूसरा 2L है, ऐसा हो सकता है, तो उसमें भी कई बार डिजेनरेसी आती है, जिसको कि हम एक्सीडेंटल डिजेनरेसी कहते हैं समटाइम्स. So we'll a few examples which is not in the slide, I will discuss in the next class. Degeneracy accidental degeneracy in this cubes and so not cubes, uh, what you say, cuboid, and you have and rectangles. So there are also some cases where you have degeneracy arising when the x and y length scale are somehow related, multiple of each other. ठीक है, आज के लिए इतना ही. So that's all for today. Thank you.